Well, welcome grade 11s to your new quad. My name is Mr. Flynn. Some of you I know already, and there are some of you that, well, I'm looking forward to meeting you, I think on Tuesday if you're watching this video. So what I do every day is I'm going to record an online lesson and post that online. Of course, I post it on a YouTube channel. And for those of you who are in class, you'll get the very same lesson, but you'll get it live, of course, and then I'll record a sort of brief lesson because you have control when you're at home watching a video, so I'll make it as brief as possible, my online lessons, but enough to obviously help you do the homework and stuff like that. The goal here is that both cohorts, whether you're at home or at school, are doing the same lesson on the same day, okay? And yeah, that way if let's say you have to self-isolate, or let's say you can't make it to school, you know, you can just do the online lesson with the other cohort that day, okay? So it's just a way of keeping everyone in the same place at the same time. And so that's how I'm gonna do it for the next couple of months. I'm gonna get right to it because I don't wanna waste your time. You know, like I said, my name is Mr. Flynn, and you should be able to see on the screen right now, it's right, you know, I'm looking at it right now, the course outline. So I'm going to show you Onenote right now. I'm going to show you where your notes are. I'm going to show you where the handouts are, and I've already put a few lessons in there. So let's get right to it. And I might disappear from the little camera view as I move over to the smartboard, but you should be able to see what I'm doing just as I scroll along here and take you through Onenote. Okay. So guys, welcome to grade 11 physics. And grade 11 physics, one of the first things that we do, just gonna move the microphone, one of the first things that we do is we look at one of the most important topics in physics, which is called Newtonian Mechanics. Now, Sir Isaac Newton was a guy that lived in the late 1600s, okay, in the early 1700s. And he really completely changed the way that we understood the laws of nature, okay? So we're going to, you know, you can't underscore his importance enough. He actually invented calculus too. It's a type of math that you'll learn in grade 12. Okay, so he's really an important character in our history, and really, the reason why we teach science today has in large part to do with the work of Isaac Newton, you know, 300, 400 years ago or so, okay? So let me show you Onenote here. Onenote is arranged like this. You'll see all of your names listed here in the margin, okay? You can post your work in Onenote. So say, for example, here, I'll pick someone in cohort B, Anthony. He never does his work, so pick Anthony here. And look, in the handouts, he's got nothing. In the homework, he's got nothing, so I guess he's not getting a head start. But you know, if you wanted to post his homework in there, and I'm gonna ask you to do this from time to time, it's pretty simple. You can take a picture if you're doing, it's a lot of math, not gonna lie, physics is a lot of math. So you're gonna be writing down a lot of equations and everything. You know, if you do that on a piece of paper, which I suggest that you do, take a picture of it and you can post it in Onenote. And sometimes an assignment will be worth a mark that way. And I'll just get you to post everything in here. I may place from time to time handouts in this handout tab. In fact, I've already got a couple of handouts here. I'm going to show you one in a moment. Yeah, so let's start. This is Onenote. Now, hopefully, if you cannot access Onenote, if you have not been able to get in, you need to log into Onenote using your OCSB student credentials, that same ones you use to access your OCSB student Gmail, okay? The same thing, use the same username and password, okay? So if it was, you know, anthony.nasrallah@ocsbstudent.ca, and then whatever your password is, okay? Mr. Flynn is great, you know, for example, then just log in using those credentials. Okay, so let's get to where the notes are. If you look up here in the content library tab, you can see it here on the left-hand side of your screen. Yeah, in the content library tab, this is gonna fill up, okay, over the course of the next couple of months, okay? You don't need to read using the content library or the course introduction. Oh, the course introduction here, I'll put that in here. I did put a little brief outline as the course introduction, so let's just go through that. As I said already, my name, okay, is Mr. Flynn. Okay, Mr. Flynn, I know you've been excited to be in my class, so you're almost there, okay? I will see you next Tuesday. Right now, I'm actually recording this on Friday, the week before, just because I got a little time to do this right now. The textbook I will give you, but you should have a link to your textbook. I included it on the Slack group chat under important links, link to the textbook. So if I have not included it yet, I will put it there. So by the time you're looking at this, you should find it there. You will get an actual physical copy of the textbook when you show up on Tuesday. But for Monday and Monday night's homework, the textbook is important, mostly just to do your homework. I will give you most of the notes that you need. You won't probably ever have to read it that much. But occasionally, we will use it for questions and stuff like that. So it's important to have. Here you can see 5 units. Now, due to the pandemic, everything's going to go really fast. We do 2 lessons a day, okay? You know, and we're going to maybe spend a little more time on these 3 units here because those are critical moving forward in grade 12, okay? So, you know, the course is front loaded with all the really important stuff, which is good. So we're just going to carry through. We're probably going to cross out this one. Several of you would have done that with me in grade 9. Okay, it's unfortunate. It's a lot of fun. I like going through it again with some of the grade 11s that I haven't seen before. But I doubt we'll have time for that. But we will probably go ahead and do this unit on electricity and magnetism, which that's kind of a fun unit to end with. Okay, so we'll probably have to strip away one of the units, and hopefully we'll get through everything else. Assessment and evaluation is a little bit different, okay, this year. As you've heard, there will be no exam, okay? So that's a good deal for you, okay? There will be an RST, but it's now worth 10%, okay? Now, tests and quizzes, I usually make worth a little bit more than that, but usually these are worth anywhere between, now that we have no exam, I'm gonna probably make these worth about 80% of your mark, roughly, okay? Then I might tweak this a little, but this is where we're gonna do a lot of that. You know, physics is a lot like math where you can do little quizzes all the time. So we're gonna do that and I'll give you lots of opportunities to get marks, okay? Labs, unfortunately, pandemic makes it difficult for us to do labs, but I'm going to do lots of demonstrations, okay? So you'll get a sense of what we would have done, okay, if you could actually touch the stuff. But unfortunately, you might have we have to limit the spread of the, you know, the COVID virus. And so what we're trying to do is get students to touch things at a minimum level. Normally, we do lots of that, but you know, it's kind of unfortunate because those are fun, but whatever, I'll do the best I can to make it fun for you, okay? Now the assignments, 10%, so we're gonna keep those at 10%, so that'll stay the way it is. So that's a little bit different this year, okay? But anyway, that's basically how you're gonna get assessed. Now, some of you were in my class in the past, if I taught you in grade 9. Yeah, so here's the deal. If you wanna write an AP exam, you know, if you're in the AP or STEM class or whatever, there is an option to do that, but it's not till grade 12. I think with all this stuff, with the pandemic going on, I really don't recommend it because you'd have to do a bunch of stuff outside of school. It's already tricky enough. So, you know, but that'd be something for grade 12. It doesn't really matter if you were in my class before. If this is something that interests you, even if I've never met you before and you never took that class in grade 9, yeah, it's okay. Like we can go through all the stuff you need to do. Whoever you are, you know, if you're interested in writing that would happen in May, okay, of grade 12. Okay, so second semester, May of grade 12 would be around the time you would do that. Okay, now if you have been in my class before, you will know I do this. I actually do online marks with Teacherease. So some of the teachers who are doing that this year, because like I've said, recommended it for them because it's a great, during the pandemic, it's a great way to stay just in touch with what your marks are. Okay, so I'm going to continue to do that. If you already have a Teacherease account, I'm not sure if you can use, I'm pretty sure you can just continue to use that one. And then I will send you an invitation to my class and you can just log in with that. Now, as far as cell phones go in the classroom, you know, we don't like distractions in the class, but unfortunately, we can't really collect them like we normally I make students put them at the front of the class, but we can't really do that during the pandemic. But I will ask that you put them away and turn off the notifications during class. Very important in a class like physics, and we go fast, so you don't want to be distracted, and make sure that that device is not distracting you, okay? So anyway, you're in grade 11, you know this already, but just to remind you of that, okay? All right, so you can read these keys to a successful year. It's pretty, you know, makes sense. Unfortunately, this one here, you won't be able to do this year, okay? But I want to highlight a couple of things. Ask questions to clarify concepts. This is really important, okay? And I want to tell you, I do not want you to email me, okay? So please do not email me. I want you to please use Slack. Slack is a group chat, okay? And if you're in my class before, we tried using Snapchat for this, but Snapchat, gotta be honest, it's kind of crappy. I don't like it very much. The chats disappear and stuff like that. Now, I really don't like it. And this one's better if you need individual help from me, you can send a direct message, okay? And you're gonna be home half the time, so use it, okay? Like I really do like giving help. If you've been in my class before, you'll know this. Okay, so yeah, feel free to use Slack anytime to send me either a direct message, which is between you and me, one-on-one, or you can use the group chat and we can help each other out. Okay, my grade 9s in semester 1, they did a great job. Like somebody posted a question on the group chat and someone else would come in with the answer even before I got there, which, you know what, that is a great way to work together. And so help each other out. Physics, you'll be doing a lot of things you've never seen before. So you're gonna need help. Don't wait to ask help when we're doing 2 lessons a day. Get the help as soon as you need it. So the whole goal here is to stay on the ball, do the homework, ask questions as they come up, never let it lag behind. And during this pandemic where we do everything at twice the pace that we normally do it, it's really important to do that. So I can't stress it enough. Get extra help. Don't be shy, okay, about asking questions. If you think you're bothering me or not, I really enjoy answering questions, okay? So if you need help, please ask. All right, now you don't have to fill this out or get it signed or anything like that. I will be, there's some online things that you have to just acknowledge that you've read these things and so on, like lab safety and stuff like that, but I'll be distributing that probably next week at some point, and I'll get you to go ahead and do that. Anyway, so you'll find this course outline in OneNote. So you can find this and read it again if you want. Let's get straight to it though. Our first unit is a unit called Kinematics, and Kinematics is a study of motion, okay? Like mathematics is basically the study of numbers, okay? A matics is a study of something. So kinematics, kina, comes from the word kinetic, which means motion, okay? And kinematics is a study of motion, and that's what Einstein did, or not Einstein. Einstein did do that, but that's what Newton did first. Newton studied motion, okay? And he discovered the laws that govern the motion of objects, and that's what we're going to be looking at. We're going to be looking at what he did. So this unit 1, this kinematics business, that's the first thing we're going to be doing, okay? And here I've listed homework for you. So today what we're going to do is just a course introduction, which I just did, but this is homework from the textbook. Now you'll notice there's a number of questions here. Now this is not like math, where like number 1 on page 6 will have A, B, C, D, E, F, G, you know, like that kind of thing. These are 1 question per number. So, you know, and it's very similar to a math class. You're gonna feel like you're kind of in a math class sometimes. That's how it is, okay? The universe is not best described with words, it's best described with numbers. And that's why physics seems a lot like a math class sometimes, okay? So we're going to do those first 2 lessons here today, okay? And cohort A, who's going to be with me on Monday, we're going to do that in class together, okay? And if you're cohort B on Monday, I tell my students, like, whether you're here or whether you're at home, you owe me some time. You owe physics class some time every day, okay? Normally you'd be in class for 2.5 hours, so you know, when you're at home, you can manage your time the way you see fit. I'll post these videos and you can watch the video, you can stop the video, you can go take a break, you can come back and look at it later. You can rewind it, like sort of go to a spot where you need that explanation heard again, okay? And this lesson today is a little bit longer, only because like I'm doing a course introduction, but normally the lessons, I'm gonna try to limit the lessons to about half hour to 45 minutes, okay, videos. And then what you're gonna have to do is just manage your time. If you're getting bored and you're losing your focus, pause it, do something else. You don't have to watch the video entirely. You could read the book. You could try using that as a resource. The video is only there to help you, okay? It's there to explain things to you in maybe a different way than the book. I think a better way, okay? I've been doing this a long time. So I think I'm in a position to help you with that. So I suggest you watch the video, take notes, okay? And yeah, follow along. All right, so let's get right to it. Now that you see what you have to do for today, you're doing lesson 1 and 2 today, okay? And there is some homework there, but there's something else I'd like to show you as well, just something I'd like you to fill in as we go along, okay? And here's the deal. On the second page here of the kinematics unit, this is really the first handout. I'm just gonna zoom out a little so you can see the whole thing. Okay, so look, before we can really talk about motion, you need to understand the words that we use, okay, to talk about motion in the first place. Okay, so distance is a word. So here's the word distance here. That is a word that we use to describe motion. Now you probably know what this word means already. Okay, and I don't have to do much to explain it to you. But what about some of these other words? Speed, okay, average speed, you know what that means? Position. Displacement is probably one that you're not used to using at all. Velocity, average velocity, and then there's acceleration and average acceleration. Now, do you know what these things mean? Okay, well, by the end of this lesson, I want you to have filled in this chart. So you can find this lesson on OneNote. What I suggest you do is go to this page, okay? So go to OneNote, look where it is, Kinematics Terms is the name of the page. Print out the page, if you can do that at home, or if you have like a tablet computer and you want to just pen in the answers, okay, fill it in. But listen, guys, please don't put like your weird like chicken scratch using like your finger to try to write it in. And then it's really messy and useless. Like take some pride, type it in, okay, or write it in with a pen. I'm going to be writing some of these in for you, but I would like you to follow along with the lesson and write it in for yourself. So if you want to print it out and write it on paper, perfect. Okay, if you can't print it out, you want to do it on the screen, well, type it in as you're watching this video, okay? Now, I will push a copy of this into each of your folders under handouts, okay? So by the time you're watching this video, that will be there for you to edit, okay, in your handout section. So like, let's say you're Anthony, okay, Nasrallah here, just go to handouts. It's not there now, but it will be by the time you're watching this video, all right? So now let me go back to where we were. Okay, so we're gonna be filling this in, and that's, you know, half of our lesson today. Okay, so let's get right to it. Now, you know, it's better for me to, how can I explain these terms to you? Well, I could just write down the definitions, but that's really boring. Okay, so I've got something else I can do instead. All right, so here's a little little guy here. It's called a running man, okay? And if you look, you can see some of the words that we've been talking about already. So for example, the word position, the word velocity, and the word acceleration. Now I wonder if I can write on this. Oh, wow. Okay, I can write on it. Okay, so here you see position, velocity, acceleration. That is so cool. I didn't think I could write on this thing. Okay, so anyway, you've got these three terms. And now you see your man up here. So here's the man. And what we're going to do is we're going to tell the man what to do. And by doing that, we're going to describe what these words mean, okay? Like, so position, velocity, acceleration. So first of all, let's get position out of the way. So here, what does position mean? Well, if you look at this, and now I'm going to show up on your screen again. I'm going to use my mouse to do this. I can change the position of the man. You see where he started at 0. And now he's at around the 4-meter mark. Okay, and then I can move him up to 6 meter mark, an 8 meter mark, and so on. Or I can move him in the negative direction. Okay, so let's say that this way, the positive direction towards his house is east, and the negative direction is west. Okay, so there's east and west. Well, if you look at the man, I'm going to put him back to 0 here. If I can get exactly 0. There, he's at 0 again. So if you look at this man, we can control his position. So what's the definition of the word position? Well, that's his location, okay, on this coordinate system. So your position is your location, okay? Like you could have your position on a map, let's say, okay, if you use Google Maps. But in this case, on the app, position is like his location on this line, okay? So it's a one-dimensional motion is all this guy is capable of, but that's it. Now I can give him some velocity also. Let's say I give him a positive velocity. Well, a positive velocity will be in the positive direction, if that makes sense. So here, I'll give him some velocity. Now he's not moving yet. So let me give him like, he's gonna move 2 meters every second, okay? So we say his velocity is 2 meters per second. Now when I press play, he's just gonna move in the positive direction at 2 meters per second. Now he's gonna hit the wall, okay, and stop at the wall. He's got no choice there. Okay, now I'm gonna pause this. So now his position is at the 10 meter mark. Okay, so velocity is the rate of change in position. Okay, that's the definition of velocity. Now, if you followed my instructions and you're filling out your little sheet, you already know what the definition of position is, right? So position is your location in a coordinate system. Okay, it's your location. Basically, just the word location, okay, relative to some point of origin. Now, in this case, the point of origin is just where he started, right in the middle. So where you're sitting right now could be your point of origin. You're sitting at home could be your house. It's your point of origin. And I could say, okay, well, what's the position of St. Matt's? And you would have to tell me, relative to your house, you would have to like look on a map and say, okay, well, it's so many meters in such and such a direction, right? And that is the definition of position. It's your location in a coordinate system of some kind. Now, velocity is when the position is changing. So if you get up and you walk around, okay, now you have some velocity. And here I'm going to give him a velocity in the negative direction. Let's make it, of course, he can move the other way, right? So let's make it -4. Now I press play, and then off he goes, and then he's going to hit the other wall at -10 meters. He'll stop there. Okay, so velocity is the rate of change in position. Okay, it's the rate of change in position. Now, as for the units, okay, the units are measured in meters for position. You can see that right here, meters for position, meters per second for velocity, and that should make sense to you, right? Like Usain Bolt can run at about 10 meters per second. Like he finishes a 100-meter dash in about 10 seconds, right? Maybe a little better than 10 seconds. So his speed is just a bit better than 10 meters per second. Let's say it's about 11 meters per second or so, okay? And what that means is in every second, he can cover 11 meters, right? And if you could do that, you'd be among, obviously, the fastest, the very top elite runners in our planet, right? That can run at that kind of speed. Now, you know what position is, you know what velocity is. What about acceleration? Well, acceleration is when you're going to change your velocity. You're going to make a change to it. Now, there's two kinds of acceleration. You could increase your velocity, okay? So let's say I start at 0 velocity. I'm not moving at all. Like the guy's not moving at all right now. But what if I set my acceleration value to, I'll set it to 2, it's a weird unit, meters per second squared. You can see the unit right there. What if I set my acceleration to 2 meters per second squared? Well, what that means is in every second, he's going to increase his velocity by 2 meters per second. So he starts with 0 velocity. Okay, see how here he has 0 velocity to start with? Let me erase some of these circles so you can see the numbers better. Watch what happens when I press play. Now watch carefully the velocity. because the guy is going to accelerate, which means he's going to change his velocity, okay? And see, the velocity is increasing all the time, okay? And that's the definition of acceleration. It's the rate of change in velocity. So what's happening is he's speeding up, right? Like in the first second, he speeds up to 2 meters per second. And then in the next second, another 2 up to 4 meters per second. So he keeps increasing his speed. It's like if you press down on the gas pedal of your car, okay, then what happens is the car will increase its velocity, okay, in the forward direction, let's say. So that's what's happening to our running man. Now, I could give the acceleration a negative number too. Let's make it -3, okay, meters per second squared. I'll just type in the number. Now, I'm going to pause this. He's got -3 meters per second squared. Now he's going to accelerate in the opposite direction, okay, in the west direction now. And if you watch what happens, he speeds up. So he goes faster and faster and faster, okay, as he moves across the line. Okay, so now you know what position means, what velocity means. So position is your location on the coordinate system. It's measured in meters. So, you know, my position relative to let's say I'm at St. Matt's right now, so that relative to the door at St. Matt's, the door of my classroom could be, you know, the door could be 3 meters north of me right now. Okay, that's its position, its location. Now, the velocity, my velocity as I get up and walk around would just be so many meters per second, and that includes direction also. I can move north, south, east, west, up, down, left, right, whatever, okay? Now, your acceleration also has direction, and I could accelerate forward, and I could start at rest and go faster and faster and faster, okay? Now, there is such a thing as a negative acceleration. Let me explain, okay, what that means. This is where it gets a little confusing, and we'll talk more about this when I see you on Tuesday. But let's say I give him a positive velocity of 5 meters per second, but then I give him a negative acceleration. Oh, let me pause this. Let me drag him back to the starting point. I'm going to give him a positive velocity of 5 meters per second, but I'm going to give him a negative positive velocity of 5 meters per second, but a -2. Okay, so here's a weird situation. He's moving in the positive direction towards his house. That's the positive direction, is towards his house. But he's got a negative acceleration. Okay, watch what happens when these two quantities, velocity and acceleration, are in the opposite direction. Watch how he moves. He slows down, and then he actually starts going in the opposite direction because his velocity is changing, right? So his velocity is getting more and more negative. Now he started with a positive number, started with +5, okay? But he's slowing down. Now watch, I can do that in the opposite direction also. So let me move him over here, stop him, okay? And let's see if this works. I'll give him a negative, actually I'll give him a positive acceleration, +3, and I'm gonna give him a negative velocity, -5, okay? And watch what happens. Actually, I'll make it -10. I'll make him, he's like Usain Bolt here, really fast, right? So now watch what happens to his velocity. He's going to start moving in the negative direction when I press play, but because he has a positive acceleration, again, he's going to slow down. See that? He slows down. That's what happens when your acceleration and velocity are in opposite directions. You slow down, okay? So when you're driving a car, some of you are going to be learning to drive now you're in grade 11. When you're learning to drive and you hit the brakes, what's happening is you've got a positive velocity as you move forward, as you're moving this way, but a negative acceleration is slowing you down, and the brakes are causing that negative acceleration. All right, so to summarize, position is your location, velocity is the rate of change in position, and acceleration is the rate of change in velocity, okay? And here you can see the units, meters, meters per second, and meters per second squared. All three of these quantities include direction. They could be positive or negative, and therefore we call them vectors. Vectors are quantities that include direction. Okay, so these three definitely include direction and position, velocity, acceleration. There you go. All right, So now let's go back to OneNote. Now that you've seen this little demonstration, I hope that was helpful. We can fill in some of these values, okay? So let's start with position. Now, what I haven't told you, okay, and I'm just gonna write it in the margin here. What I haven't told you yet is there are quantities called vectors, and vectors are quantities that include direction. And I'm sure you love my handwriting, okay? So please don't shower me with compliments on my handwriting. I know it's beautiful, okay? Now, scalars are quantities that do not include direction. Okay, so please keep that in mind. Some quantities include direction, some don't. For example, if I run a marathon, let's say it's 42 kilometers. I'm horrible at running marathons. I would never do this, but anyway, I'm not crazy. Okay, let's say it's 40 kilometers, whatever a marathon is. Okay, the full marathon. That's the total distance. Notice we don't mention the direction, like who cares, right? Who cares if it's a, like, you know, usually you start at some point and then you run some type of loop around the city. And then when you come back, you've run a total of 40 kilometers, but it's some type of loop, right? So the direction is changing all the time as you're running through the course, but we don't really care what the direction is. So distance in the marathon, distance is actually not a vector, okay? So here, distance, speed, okay? These are actually scalars. They do not include direction. Now, there are lots of quantities that don't include direction, like your height, for example. Okay, so let's say you know, Laco. Laco is not a very tall guy. Well, I guess he's tall enough, right? Okay, so Laco, maybe he's like what, 6'5" or something, 6'6". I don't know. I just know he's taller than I am. So we wouldn't say that he's 6'6" north, right? Or that he's like, you know, 195 centimeters up. We don't say up. Like his height would be the same if he was upside down or lying on the floor. That doesn't change the length of his body, right? So length, width, height, and so on, these are not vectors, right? These are just, you know, sort of like distance. It's just this, how long is, you know, that body, let's say, okay? How tall is that body? And that would not include a direction. So there's lots of quantities that don't include direction like that. Your mass, you don't say, oh, I step on a scale and look, I'm 180 pounds west. Okay, well, I'm speaking nonsense because you wouldn't include a direction with that, right? So those are scalars. Distance, speed are scalars. There's a bunch of other ones, mass, volume, density, right? All the dimensions, length, width, height, and so on, width, you know, height, you know, etc. These are all scalars, temperature, and so on. But there are some things, and it's a much shorter list, some quantities that do include direction, okay? Namely, okay, and these are vectors, position, velocity, another one called displacement, and then finally acceleration. These quantities do include direction and therefore they're vectors. And that's the full list, okay? There are a couple of other ones that include direction, like there's one called jerk. Okay, we'll talk about that later. That's actually a physical quantity and it does include direction, but I don't want to confuse you, so we'll talk more about that when I see you on Tuesday, okay? All right, so now that we've got the gist of it, let's fill in this thing, okay? I don't want to do it all for you. I know I asked you to do it, but I'll just give you some sense of it. I already told you that distance was a scalar, and it is a measure of the total number of length units traveled. So say you're traveling from here to Toronto, that's 400 kilometers. Notice we don't include the direction. That's why it's a scalar. Okay, we don't include direction there. It's just how long was the path. Okay, one lap around the track is 400 meters. How long is that path? Well, it's 400 meters. The direction is changing because it's a curved path. So, you know, we don't really care what the direction is. We just say it's 400-meter path, and that's it. Now, here's an example. We use D as a variable for distance. Okay, so D is a variable for distance. The unit is meters, is the standard unit. The Americans might use feet or yards or miles or whatever. For us, keep it simple, we use meters. And kilometers if it starts getting too big. That's just 1,000 meters, right? So we use the metric system. There's an example, D is equal to 250 meters. Now, what about speed? Well, speed is also a scalar. So I'm just going to write the letter S. Speed is a scalar, okay? And it's the rate, the definition is the rate of travel, okay? The variable used is actually a V. Now, that gets confusing. Why don't we use an S? Good question. I'm not sure, but we use a letter V, okay? I think because of it's closely connected to velocity, right? But it doesn't mean the same thing. It actually doesn't mean the same thing. Okay, it's not just the same thing and one includes direction and the other one doesn't. Okay, so anyway, the units of speed are in meters per second. And an example could be like Usain Bolt, right? Here, let's make it 11 meters per second. Okay, and there you go. All right, so now that you've seen that, what about average speed? Well, if speed is a scalar, then average speed is also a scalar. And this is, it's going to sound weird, but it's the average rate of travel. Okay. We write V with an AV beside it like this. Its unit is still meters per second. Now here, under an example, I'm going to show you, because your textbook questions will ask you, what is the average speed? Okay, so let me give you an example of that. Okay. Let's say I travel from here to Toronto. The distance is 400 kilometers. That's the distance of the road. And my time is 4 hours. So what's my average speed? Well, I would actually just divide those two numbers. The total distance divided by the time. And my units won't be meters per second. They'll be kilometers per hour, but that's an alternative unit that you're allowed using. Okay, it's not a standard unit, but so my point is you take the total distance, divide by the total time, and that will tell you someone's average speed. Okay, let's forget the trip to Toronto for a second. Let's say you take one trip around the track. Well, that's 400 meters, right? And let's say like maybe you started out fast, but then you started getting gassed, okay, as you're running around the track, because you can't just sprint around the track. You have to pace yourself a little bit. Otherwise, you will run out of gas. Okay, so let's say it takes you, I don't know, 20 seconds. So that's too slow. Let's say it takes you, let's see, 4 meters per second. It's going to take you at least 40, but let's say it takes you 80 seconds. Okay? You can't go faster than 10 meters per second because you're not Usain Bolt. All right, so now you have these numbers. You can just take out a calculator here and just go 400 divided by 80 is 5. And so I should know that, shouldn't I? Anyway, I'm lazy. 5 meters per second. Now that's your average speed. Now, it doesn't mean you're always traveling at 5. See, that's why we call it an average. You could have started out sprinting and then slowed down, okay? Or you could have started off slow and sped up. In fact, you could be moment to moment, you could be changing your speed all the time, but it took you a total of 80 seconds to do 400 meters, and so that's your average speed. You get it? Just total distance divided by total time. Okay, very straightforward. All right, so you're with me here? Now, here's the deal. I've already told you what this one means, what that one means, and what that one means. We did that on the app, okay? So position, we actually use the letter D, but we put a little vector sign on it. It's got a little hat on top. You've probably never seen that before. So here you go, here's your little vector hat. So you put that on your head, a little arrow over your head, half an arrow in this case. It means you're a vector, okay? I actually shouldn't write it here. I should write it here. And here, I should tell you this is a vector. So I'll use the letter V. And it's your location, right? Okay, in a coordinate I'll just write coordinate abbreviated system. And that is what position means, okay? We use meters. So if you're, you know, if you watch a military movie or something, sir, what's the enemy's position? And they'll say 350 meters west. You get it? Like, it's a vector, so you include the direction. If they just said 350 meters, we don't know their position. What direction is that, right? Yeah, we use the letter D because it's kind of connected to distance. I think that's why. And you can just write D equals 350 meters. And here's how we write direction. That means west. Okay. So there you go. There's an example of position. Now, displacement I didn't define for you. So I'm going to do that for you now. Displacement is a vector. So you're not confused. It's a vector. Okay. And it is a change in position. Okay. So let's say you're standing in one spot and then you move to another spot. Well, now you've changed your position. So we call that a displacement. And you know, in math, the little triangle means a change. It's a delta. It means change. And it's a Greek letter, actually. So when there's a change in something, we just use the Greek letter delta. So delta D means the change in position. It literally, this sentence here is represented mathematically by that right there. Now, of course, it's also measured in meters. So what was your displacement? Well, I moved 3 meters north, okay? So here I could write delta D equals 10 meters. I'll make it 10 meters. And that means north in this case. I think you understand. Capital N means north. Okay, and we put it in square brackets. And so your change in position. So I could have started at 350 meters west, but then I moved north, okay, from that position, another 10 meters or whatever. And so that was my displacement, okay, 10 meters north. All right, well, moving on, I'm gonna let you fill in velocity. Remember, velocity is the rate of change in position, but I'm gonna tell you that that is definitely a vector. And we use the letter V with a little hat on it, okay? It's also measured in meters per second. And I'm gonna let you fill in the 2 blank boxes as your little assignment. Now, average velocity is also a vector. Okay, it's the average rate of change in position. Okay, that's the definition of velocity. So we use V like this. It's starting to look like speed and average speed, but it's with the hat makes all the difference, right? That little hat means it's velocity, not speed. It's also measured in meters per second though. Okay, and here's the thing. The average velocity is not the total distance divided by time. Instead, it's the total displacement divided by total time, okay? So it's the total displacement divided by the total time. That one gets a little weird, okay? So let's say you make 1 lap around the track. Okay, now you're back where you started, right? So what's your total change in position? Well, you started, let's say you start, you know, where the bleachers are. You do 1 lap. Here, let me draw a little diagram. Let's say this is the track outside the school and the bleachers are right here. Well, so you started here and you do a little trip, do 1 little trip around and you go back to the starting point. Well, your distance, your total distance, 400 meters. Okay, that's how big that oval is that you just ran. Okay, but your displacement is 0. Because you're back where you started. So that's the same position. There's no total change in position. You started at the bleachers, you ended at the bleachers. So you're back where you started, okay? So that's called a round trip. And in the all round trips, your total displacement is 0. Like let's say you start every morning, you get out of bed. Then you end every day by going back to bed. So what's your total displacement on the day? Well, it's always 0, right? As long as you start and end in your bed, your total displacement is 0 for that day, okay? And that's true every day, okay? And that's how it works, okay? So this total displacement is a little more tricky. You have to look at where they start and where they end, and then you go from there, okay? Let me give you another example of total displacement. Let's say you start here. We'll make this one-dimensional, okay? And let's say you travel east like that, 10 meters, okay? And then now you're here. But then you turn around and you go back. I'll change color here. You go back this way, okay? And you end right there, okay? So you end right there where the red X is. And this distance from here to here is -5 meters, okay? So here's the deal. You started at 0, right there. You travel 10 meters over here to the 10-meter mark, okay? So you travel 10 meters that way. Then you turned around and went this way, okay? And you actually walked 15 meters in the opposite direction, past your starting point, to end where our little X is over here, okay? So what's your total distance? Well, the total distance you traveled would equal 10 plus 15, right? It's equal to the black line. That's this line here, that's 10 meters. But then you turned around and you followed the red line all the way over here. Well, the total length of that yellow line that I just drew would be 10 plus 15, which is 25 meters. That's your total distance that you walked, right? As you're pacing back and forth. But your total displacement only depends on your starting point and ending point. So you started right here at that spot, but you ended over here at that spot. Well, you're 5 meters from your starting point in the negative direction. So your total displacement will be -5 meters. And that's the one where people get confused, okay? So anyway, that's the difference between distance and displacement. Distance is easy, it's intuitive. You're used to thinking about it. If you're a runner or something like that, you get it. Like this is how far you've walked, right? Okay, so, and you don't really care about changing directions. But displacement is different, okay? Displacement only depends on where you start and where you finish. So keep that in mind, okay? Now, we've left one out here. Let's talk about acceleration. So here, acceleration is also a vector, okay? And it's the rate of change in velocity. We talked about it already. I'll let you fill it in. We use A, okay, for acceleration, not surprising. The units of acceleration are meters per second, because like if I'm changing my speed at 2 meters per second every second, then it's 2 meters per second is my rate of acceleration. It's a mouthful, but that's the same as meters per second squared. So from now on, I'm going to use that unit, meters per second squared, okay? And, you know, an example could be A equals 3 meters per second squared west. Okay, so you're accelerating in the west direction, say driving your car. Now, average acceleration is also a vector, okay? And it's the average rate of change in velocity, okay? We use A with an average written beside it. It's still meters per second squared, that hasn't changed. And here, to calculate average acceleration, you do the change in velocity divided by time. Okay, so now if you look at this chart, we filled in, here, I'll put this as an example too. Let's say it's 11 meters per second east this time, okay, like that. So we filled in this chart with some examples. So I filled most of it in for you now. You just have a few blanks left to fill in on your own, what I showed you with the Running Man. But yeah, take a look. I mean, these are the words that we use to describe motion, okay? So if I say distance, speed, average speed, position, displacement, I need you to understand what these words mean, and they need to become sort of second nature to you. So if we're going to look at how objects move, which is what kinematics is all about, you need to know what a vector is, what a scalar is, okay? You need to know what the definition of all these terms are, and we're going to write them mostly mathematically using these variables that you see here, okay? Anyway, I know I'm throwing a lot out at you, and I know these videos can get quite dry and boring, but like I said, you can pace yourself, pause the video, walk away. Okay, come back to it, continue later. It's up to you. All right, so I just have one other thing to show you, okay, and we'll see how far we get here. I don't want to do too much of this, but I've already included some notes for you. I might just get you to read them, and then I will go over this with you when I see you on Tuesday. But let me go back to the Running Man for a moment. Okay, there's another way we can look at this. I'm just going to erase what I drew, and then I will show it back in your screen again. And what I'd like to do is just reset everything. And then instead of showing you numbers, I'd like to show you a graph, okay? So take a look at the Running Man's position here, okay? And I want to see if I can, yeah. All right, so check it out. Look at just the blue graph, please, at the top. So in the blue graph, all I'm doing is taking the Running Man and making him run, pace back and forth to his house, over to his tree over here, okay? Now he's just sitting there. And look at the position time graph. When he's just sitting still, look what happens. In the position time graph, that it's just a horizontal line. He's holding the same position over time, right? So now he's moving in the positive direction towards his house. Okay, and now he sits at his house for a while, okay? And so look at the blue line. He turns around and goes the other way, okay? You get the idea, right? So the blue line that you see here describes the man's position as it changes with time, okay? And so that's a position time graph. And I just wanna help you understand how we read a position time graph, okay? So like if you look, all the man can do is move up to 10 meters from the starting point, from 0, or he can move, you know, to -10 if he goes west, +10 if he goes east, that kind of thing, okay? So if we were to graph out his movements, okay, that's what a position time graph is all about. Now there's other graphs here I'd like you to ignore. Actually, I wonder if I can close these. There we go. Let's just focus on the one we're interested in today. Perfect. Okay, so there's your position time graph. So, you know, you could tell where the guy is at any moment in time, right? So when was he close to his house? Well, his house is at 8 meters. So here, he was at his house here for a moment, but then he turned around, he went back to the tree over here, okay? Here's where he passes through 0 on his way to the tree, okay? He's at 0 right now. Here he stayed at the tree for what seems like several seconds, okay? Like from about between 6 and 12 seconds or so. Then he headed back towards his house. He stayed at home for a couple of seconds before he returned to the -3 position, which you see right here. So you understand what a position time graph tells you. It tells you his location over time, okay? Now, in the homework, I have for you a position time graph, and I just want to tell you, like, I included a couple of things here that I would like you to read. I can read them with you if you want, but anyway, the value on a position time graph tells us, of course, his position at any given time, right? How do you find the displacement? So remember, the word displacement means change in position. So if we go back to the Running Man here for a moment, and I say, okay, what is his change in position? Like, okay, here, let me erase these lines. So let's say here, he starts at the tree. So he starts here, and he goes to his house. What's his change in position, okay, between those 2 points? Well, he started at -8. He ended at +8. So what's his change in position? Well, the change in position would be d2 minus d1, okay, or these are vectors, so all vectors like that, or it would be 8 minus -8, which is equal to +16 meters, and that's his change in position. Okay, you with me here? His change in position. So it's just like finding delta y in math class. Does it make sense? Delta y. like, you know, when you're finding slope, delta y over delta x, so ringing a bell. Well, you're going to be doing that here too, okay? So anyway, finding the total distance. The distance is a bit tricky, okay? But I'll have to explain this one to you. Distance is tricky when the guy's moving back and forth like that. So why don't we come back to this one, finding the total distance. We'll come back to that when I see you on Tuesday. But one thing I would like you to do is slope, okay? So the slope of this line is the definition of velocity. And the reason why is because look at what happens when you find slope on a position versus time graph. You're going to go rise over run. You know how to find slope. Okay, it's rise over run. Well, that doesn't change because it's physics. It's the same thing. Well, delta D is the rise. Because it's position on the y-axis. And delta t is the run. And so that is the definition of velocity. Okay, so it's true by definition that the slope is equal to the velocity. Okay, so this is sort of a key point. The slope of the line on a position time graph is equal to velocity. Now, we don't have a lot of time for me to explain this to you. You haven't learned this yet in math. And in physics, sometimes I have to teach you things that you'll learn eventually in math, like in grade 11 or 12 or whatever. But I might as well explain this to you now. What happens if you have a curve on a position time graph? Is there a way to find slope on a curve like this curve you see here that I just sort of highlighted with the rainbow color? Yeah, like let's say I want to know the slope right there at this spot. Well, a curve, okay, sorry, I switched screens by accident. A curve is a line with a changing slope. Okay, that's the definition of a curve mathematically. And so how do we find slope on a curve? Well, we pick a point, and what you do is you draw what's called a tangent line. It has nothing to do, well, let's just say it has nothing to do with the trigonometric function called tangent, okay? It's just the slope of that green line. The green line touches my curve at that spot. And then by measuring the slope of the green line, just rise over run on the green line, I will know the slope of the curve at this point here, okay? So we call that instantaneous velocity, the velocity at a point. Okay, so that's what slope of tangent means. But again, I will explain this one to you better when I see you on Tuesday. Now, I did have some questions here, okay, that you might want to try, okay, for homework. But I would suggest you leave this sheet here. I'll push it into your folder, but I would suggest you leave this alone, okay? And then we'll talk about it in class. It'll seem too confusing, I think, for you to do it by yourself. I did put answers here though. So if you want to try it, go ahead. I did put some answers there. You'll see them in brackets right after the question. Okay. All right. So guys, that's enough for today. And I'm sorry this one took so long. This is a longer lesson than normally I would do. Normally I keep them brief, but because it's the course introduction, this one's a bit longer. So I'm sorry if I've bored you to tears, but hey, it's COVID teaching. So get used to it. I hope you appreciate me posting lessons like this though. And like I said, pace yourself. Don't think you have to sit there the whole time. If you start losing your focus, come back to it, take a break, whatever it takes, like, you know, get a cup of coffee if you drink coffee, you know, that kind of thing, and then come back to it. Okay, so what I'd like to point out to you is in the course outline, we have now covered lessons 1 and 2, where I told you what average speed and average velocity meant. We talked about what vectors and scalars were. We did a course introduction, defined terms that we use to describe motion, and we just started talking about position time graphs. Okay, so please attempt this homework here, okay, from the textbook. Use the online copy of the textbook until you get your own copy. And then, you know, if you have questions, feel free to ask me, okay? And please don't be shy, and please don't hesitate to ask. All right, so that's it for today, guys. I hope you know, enjoy your couple of days off that you've had here, okay, heading into a new quad. It goes very fast, okay, so yeah, I'm looking forward to meeting you on Tuesday. And until then, talk to you soon.